This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 6, Lesson 1, Control Concepts Part 1, Sensors, Actuators, Valves, and Dampers. Every HVAC control loop is the same three parts: a sensor that reads, a controller that decides, and an actuator that drives a final element, a valve or a damper. We'll read the three valve flow characteristics, see why equal percentage is the HVAC default, size of valve's flow coefficient, and the trap this whole lesson turns on. Keep that sizing completely separate from the cavitation choke point check. Concept 1. The control loop. A closed or feedback loop is three links driving a controlled variable toward its set point. The sensor and transmitter measure the variable and send a standard signal, 4 to 20 milliamps, 0 to 10 volts, or a DDC protocol, and we judge it on sensitivity, repeatability, and response time. The controller compares measurement to set point and computes an output. The actuator strokes the controlled device, the handbook's third link, a control valve on water or steam, a control damper on air. Each actuator has a normal position on loss of power: fail open, fail closed, or fail in last position, chosen so the failure is the safe one. A heating valve fails open to prevent a freeze. Concept 2. Valve flow characteristics. The inherent characteristic is how flow tracks stem stroke at a constant valve pressure drop. Quick opening gives most of its flow in the first bit of travel. That's on-off service. Linear makes flow proportional to stroke. Equal percentage changes flow by an equal percentage for each equal step of stroke, so most of the flow arrives near full open. Equal percentage is the HVAC default. A coil's heat output is already nonlinear with flow, and this curve cancels that nonlinearity to give near-linear, stable control across the whole stroke. Setup, authority, and gain. Valve authority is the valve's share of the branch's total resistance, taken with the valve wide open. Open valve resistance over total system resistance times 100. Aim for roughly 25 to 50%. That's design practice, not a printed handbook number. That resistance is just the valve's design drop. Our valve, sized for a 16 psi drop in a branch that drops 40 total, has an authority of 40%. Healthy. Too low, and the fixed pipe loss swamps the valve. Its installed curve distorts, and it loses control near closed. Valve gain is the slope of the flow curve, percent change in flow over percent change in stroke. On an equal percentage valve, that slope deliberately rises with stroke, canceling the coil's falling gain, so heat output tracks the signal nearly linearly. Good authority keeps the installed curve close to that inherent shape. Setup. Two look-alike valve formulas that get swapped on the exam. The flow coefficient sizes the valve. CV equals flow over the square root of the pressure drop, for 60-degree water in gallons per minute at a 1 psi drop. For anything else, multiply by the square root of specific gravity. The cavitation formula finds the choke point. Allowable delta P equals Km times inlet pressure minus vapor pressure, with Km 0.7 for half to 2-inch valves and 0.5 for the larger sizes, and both pressures are absolute. CV answers how big. Allowable delta P answers how much drop before the flow chokes and the valve cavitates. Our givens: 40 gallons a minute of water, 16 psi available, a 1-inch valve, inlet 60.5 psi absolute, vapor half a psia. Solve. Size the valve. Feed the required flow and the drop the valve is allowed to take into the sizing formula. CV equals 40 over the square root of 16. 40 over 4, 10. The non-water form gives the same thing here. 40 times the square root of 1 over 16, which is 40 times a quarter, 10, because specific gravity is 1 for water. So select a valve rated near CV 10, the gallons of 60-degree water it passes at a 1 psi drop, a pure geometry number. Then confirm the characteristic is equal percentage and the authority is healthy. Solve. The cavitation check. Now a completely different question. At this drop, will the valve choke and cavitate? Use the choke point formula, not CV. Allowable delta P equals Km times inlet minus vapor. 0.7 times 60.5 minus 0.5, which is 0.7 times 60, 42 psi. The actual working drop of 16 psi is well under that, so flow still rises with drop, and the valve does not cavitate. Push the drop past 42 and the flow chokes. No extra flow, plus noise, erosion, and loss control. And mind the km size split. 0.7 for half to 2 inch, 0.5 for 2.5 to 6. One more sizing rule before the dampers. Steam valves. Water uses flow over root delta P, but steam gets its own printed pair, with flow in pounds per hour. At 15 psig or less, size on a drop equal to the supply pressure. Flow over 2.11 times the root of inlet squared minus outlet squared. Above 15 psig, the critical drop governs, 42% of the absolute inlet, and the formula collapses to flow over 1.6 times the inlet pressure. Past that critical drop, the valve is choked, and a lower outlet pressure buys you no more steam. Concept: control dampers. Dampers are the airside final element and follow the same logic as valves. Two-position versus modulating, just like valves. Parallel blade dampers rotate their blades together. They deflect and mix air streams, so they're preferred in a mixed air section. Opposed blade dampers rotate adjacent blades in opposite directions, giving a more linear, controllable throttling characteristic. And authority carries straight over, open damper resistance over total system resistance, times 100. A low authority damper does most of its work in the last few degrees of travel, the airside version of a valve losing control near closed. A few more definitions the exam likes. Two-way globe valves come single-seated for tight shutoff, or double-seated, which balances the pressure and cuts the actuator force but won't shut off tight. Butterfly and standard ball valves are two-position only. Characterized ball valves can modulate. Three-way valves either mix, 2 inlets, 1 outlet, or divert, 1 inlet, 2 outlets, and mixing is generally preferred. Rangeability is the ratio of maximum to minimum controllable flow. And an electric heater must carry a minimum airflow switch, plus 2 high limits, 1 manual reset and 1 automatic. Low airflow keeps the coil off. Traps. 4 ways this bites. 1. CV sizing is not the cavitation check. CV sizes the valve. Allowable delta P is the choke point where flow stops rising. Same page, different questions. A big enough CV still cavitates if the drop exceeds the allowable. 2. The cavitation pressures are absolute, PSIA not PSIG. Forget to add atmospheric to a gauge inlet and the allowable comes out too small. 3. Authority is the valve's share of loop resistance. Target 25 to 50%. An oversized, low-authority valve lets the pipe dominate and loses control near closed, no matter how correct the CV. 4. Pick the characteristic for the load. Equal percentage is the default because it cancels a coil's nonlinear heat output, while quick opening is on-off service. Put the wrong one on a modulating coil, and control gets twitchy at the low end. Quick recall. A loop is sensor to controller to actuator to valve or damper, each actuator with a safe normal position. Fail open, fail closed, or fail last. The 3 inherent characteristics are quick opening, linear, and equal percentage. Authority is the valve's share of loop resistance. Aim 25 to 50%. Gain is percent flow over percent stroke. Size with CV equals flow over the square root of the draught times the square root of specific gravity for non-water. Check cavitation with allowable delta P equals Km times inlet minus vapor, both absolute. Damper authority mirrors valve authority. Golden rule. Equal percentage is the HVAC default, and CV never tells you whether the valve will cavitate. Next up, Lesson 2, Control Loops, PID, Temperature Reset, and the Economizer. We built the loop and sized its final element. Now we tune how the controller decides. We'll cover proportional band and gain, the offset that proportional control leaves and how PI reset erases it, what derivative adds, open versus closed loops, temperature reset control, and the economizer, where a mixed air temperature is just a flow-weighted average of outdoor and return air. Everything's at PEPrepEngine.com. Cheat sheet, work solution, and a quiz attached here. If this course is helping you get ready for the PE, subscribe so others can find it too.
The full study guide with every equation and common exam trap is free at PEPrepEngine.com Link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.